This is the A-10 Thunderbolt. While most aircraft are designed to avoid getting shot, this one was designed to eat bullets and missiles for breakfast, then ask for seconds. It does this thanks to multiple systems that literally no other aircraft has been able to replicate before or since. In preparation for today's fire mission, the pilot and ground crew first go through a series of pre-flight checks. When first looking at the Warthog, as pilots call it, the nose bulges forward around a cannon that dominates the entire front third of the fuselage. That weapon is the GAU-8 Avenger, a 7-barrel, 30mm Gatling gun stretching over 19 feet from breech to muzzle, with the gun's weight making it an eligible contestant for my 600-pound life. It is this system that will be the star of the show for today's gun run. Loaded with over 1,100 pounds of ammunition, the entire system weighs just over 4,000 pounds, roughly 16% of the aircraft's empty weight. Remove the gun for maintenance and the aircraft tips backward onto its tail because the mass distribution assumes the weapon is always present. Ground crews install a jack stand under the tail before disconnecting anything. What you're seeing here isn't a gun attached to an airplane. It's an airplane built as a delivery system for this gun. And getting that gun to the target requires engines positioned where enemy fire can't reach them. Twin General Electric TF-34 GE100 turbofan engines hang off the rear fuselage in separate housings, each producing 9,000 pounds of thrust. The placement looks crude, pods bolted on as afterthoughts, but the positioning keeps pilots alive. Mounted high and aft, the aircraft's body shields them from ground fire coming up from below. The exhaust nozzles angle upward, directing heat away from infrared seekers, heat-seeking missiles that lock onto hot engine exhaust. A missile that can't see the heat can't track the aircraft. Then there are those wings. These straight wings look outdated next to swept-back fighters, but the shape serves a purpose. Swept wings trade low-speed handling for high-speed performance, and the A-10 needs the opposite trade. The straight wing configuration lets the aircraft turn tight at 300 knots, fly as slow as 140 knots without stalling, and circle back for another pass when the first one wasn't enough. For troops on the ground waiting for fire support, that slow-speed maneuverability means the difference between help arriving and help overshooting the battlefield. The wings sit low on the fuselage, allowing for 11 hardpoint stations capable of carrying 16,000 pounds of external weapons. About 95% of the airframe uses aluminum alloys with sections riveted together using flat plates interchangeable between left and right sides. The designers avoided composite materials on purpose. Composites shatter on impact. Aluminum is like the Play-Doh of metals. It bends, tears, and keeps flying. Damage that would destroy a carbon fiber structure just puts holes in this one. But aluminum alone won't stop a 23mm cannon round. For that, the engineers wrap the cockpit in the infinity stones of the aviation world. 1,200 pounds of titanium armor wrap around the cockpit in a continuous shell that maintenance crews call the bathtub because the shape earns the name. But here's what makes it special. The armor is not a single piece. It's multiple plates ranging from ½ an inch to 1.5 inches thick, with the thickness of each position determined by studies of where enemy rounds are most likely to come from. Thicker where gunfire concentrates, thinner where it rarely hits. Every fraction of an inch calculated to stop what's coming without adding weight that isn't needed. This titanium stops 23mm cannon rounds, the caliber of Soviet-designed anti-aircraft guns built specifically to knock down low-flying jets. A burst that would shred an F-16 cockpit pings off the bathtub like a spitball. But stopping the round isn't enough if fragments spray into the cockpit afterward. Any plate facing the pilot is lined with multi-layered nylon spall shells that catch shrapnel if a round partially penetrates, the difference between a bruise and a knock at the door back home. However, this protection extends beyond the pilot because protecting only the human means nothing if the aircraft becomes uncontrollable. The bathtub wraps around to shield the flight control linkages too. So the same armor that keeps the pilot breathing also keeps the aircraft flyable. Survive the hit, but lose the controls? You're still toast. The engineers thought of that. A plane without fuel is also like a giant lawn dart. So the fuel system follows the same paranoid logic. 4 main tanks cluster near the aircraft's center of gravity rather than spreading through the wings where they'd be easier targets. Each tank sits inboard of the outer skin with structural space between, meaning a bullet has to punch through the fuselage twice before reaching fuel. Even then, the tanks don't rupture like normal fuel cells. They use reticulated polyurethane foam, an open cell material filling the interior that catches fragments and chokes off fuel spray before it can fill the fuselage with flammable mist. Self-sealing bladders made of vulcanized rubber close around punctures the way skin closes over a wound, swelling when the fuel touches them to plug the hole. When damage exceeds what sealing can handle, one-way check valves slam shut to isolate the compromised tank. 2 emergency sump tanks hide near the aircraft's core. 230 miles of fuel even if every main tank gets shredded. That's the difference between ejecting over enemy territory and limping back to friendly airspace. This philosophy extends to parts pilots never think about until they fail. The landing gear handles rough fields and broken concrete because the A-10 was designed to operate from highways if runways get cratered. Spare components are interchangeable left to right. Same engines on both sides, same landing gear assemblies, same tail fins. So maintenance crews with half a parts inventory can keep aircraft flying by swapping components between damaged jets. So essentially, the A-10 is like that old beater you give as a first car to your kids. No matter what abuse they put it through, it'll keep on keeping on. The pilot finishes his walk around and climbs the boarding ladder. But despite all these precautions, early test pilots discovered something the engineers missed, a threat from inside the aircraft that can destroy both engines mid-attack. General Electric built these engines with priorities that seem wrong for a combat jet: efficiency over raw power, endurance over speed. The TF-34 is a high bypass turbofan with a ratio of 6.2 to 1, meaning for 1 part of air going through the hot core of the engine, 6.2 parts of air go around it. For comparison, a fighter jet usually has a ratio of 1 to 1.5. This reduces maximum thrust but dramatically improves fuel economy, and fuel economy translates directly to time on station. This matters because the A-10 can loiter over a patrol area for nearly 2 hours while faster jets burn through their tanks in minutes. When a ground element calls for help, they don't need an aircraft that arrives fast and leaves immediately. They need one that shows up and stays until the threat is neutralized. Loiter time saves lives. Speed doesn't. The efficiency creates a second advantage. Less fuel burning means cooler exhaust, and cooler exhaust means heat-seeking missiles have a harder time locking on. The engine placement behind and above the wing hides what heat remains from the threats looking up from below. Ground crews can also swap a damaged fan blade through an access slot without pulling the whole engine. 14-stage compressor, annular combustion chamber, and turbine sections are modular, which matters when you need the aircraft back in the air before the next call for fire support. But those engines face a problem from inside the aircraft, from the weapon they exist to deliver. The GAU-8 produces enormous volumes of gas when it fires, and that gas contains almost no oxygen. Jet engines need oxygen to sustain combustion, so gun gas flowing into the intakes chokes the fire that keeps the turbine spinning. Early flight tests discovered this the hard way when pilots fired the cannon and both engines flamed out simultaneously. Loss of all thrust during a diving attack run with the ground rushing up. Imagine that for a second. You're in a dive, nose pointed at the earth. You pull the trigger to do your job, and suddenly both engines go silent. The ground is getting bigger fast. The solution was to wire the engine igniters directly to the gun trigger. Every time the pilot fires, the igniters activate automatically. If a gun gas chokes the combustion, the engines relight before the pilot notices anything wrong. This system handles a potentially fatal problem faster than human reflexes can respond. With both engines running and systems normal, the pilot taxis toward the runway. But before takeoff, one more system requires verification: the redundancy that kept Captain Kim Campbell alive when everything else failed. The A-10 rolls toward the runway with the nose wheel, which is strangely off-center by exactly 11 inches to the aircraft right to accommodate the GAU-8 Avenger cannon, which must be centered for accuracy and stability. But it's also sitting so far forward that turning requires planning 2 moves ahead. The taxi provides time for the flight control check that determines whether the redundancy engineering actually works. The pilot moves the stick left, the ailerons respond. Stick right, response. Stick forward, back. The elevators cycle through their range. Rudder pedals left, right. Twin tails swing in opposite directions. Every input produces the correct output. The aircraft is ready. 2 completely independent hydraulic systems power every control surface on the aircraft. System 1 and System 2 each connect to the ailerons that roll the wings, the elevators that pitch the nose up and down, and the rudders that swing it left and right. Each system uses separate pumps, fluid reservoirs, and lines routed through different parts of the airframe. A hit that destroys one system leaves the other untouched, and the pilot notices nothing but a gauge dropping while the aircraft keeps responding normally. The ailerons stretch across nearly half the wingspan, far larger than typical fighters, to provide control authority even at the slow speeds where the A-10 operates. These ailerons split vertically and double as speed brakes. Both halves can open simultaneously above and below the wing to create drag without rolling the aircraft, letting the pilot slow down fast for weapons delivery. But here's where the engineers got paranoid in the best way possible. They assumed both hydraulic systems might fail. Behind them sits a manual reversion system, a mechanical backup connecting the control stick directly to the control surfaces through cables and push rods with no fluid pressure required. Switching to manual makes the aircraft dramatically harder to fly because the pilot's muscles must move surfaces that hydraulics normally move. But controllable beats uncontrollable every time, as one pilot actually proved in combat. In 2003, Captain Kim Campbell took ground fire over Baghdad that shredded both hydraulic systems and punched hundreds of holes through the aircraft. She lost all fluid pressure. The flight controls went manual. She fought the stick for an hour, muscles straining against the surface designed for hydraulic power, and landed the aircraft. She walked away from a situation that would have been fatal in any other cockpit. The pilot now lines up on the runway and advances the throttles. 18,000 pounds of combined thrust pushes the aircraft forward. The nose lifts at rotation speed. The gear retracts, and the A-10 climbs away from the airfield. Now the weapon that justified every compromise demands attention. The aircraft levels at patrol altitude and the pilot runs through the weapons check. Master arm, safe for now. Gun switch to arm. The HUD confirms what's loaded. Over 1,100 pounds of alternating, armor-piercing, and high-explosive incendiary, coiled in the drum behind the cockpit and waiting to feed. But here's the problem with a gun this powerful. Fire it like a normal weapon and the barrels melt. 7 barrels sit in a rotating cluster below the pilot's feet. When the trigger goes down, they won't fire simultaneously. Instead, they rotate through the firing position one at a time, each barrel getting a fraction of a second to cool before cycling back around. It's the same principle as rotating tires on your car so they wear evenly. Except instead of rubber meeting asphalt, it's controlled explosions happening 65 times per second. And that rotation has to be perfect. Inside the gun, each barrel has its own bolt riding a stationary cam path. As the assembly spins, that cam forces each bolt through a complete cycle. Load, chamber, lock, fire, unlock, extract. All in a single revolution. Miss a single step in that sequence and the whole system jams. 65 revolutions per second. 65 chances for something to go wrong every second. The ammunition drum feeds rounds through a linkless system. Linked ammunition, rounds connected by metal clips, can jam if a link bends. Linkless eliminates that failure mode entirely. Spent casings cycle back into the drum rather than ejecting overboard because throwing that much brass to the aft would shift the aircraft's center of gravity and could send debris into the engine intakes. But compared to what those rounds are made of, the brass casings might as well be Jake Paul punches. The armor-piercing rounds use depleted uranium penetrators. Uranium with most radioactivity removed but none of its density. Depleted uranium is 70% denser than lead. And unlike steel or tungsten, it self-sharpens on impact. When a penetrator hits armor, the outer layers shear away in a process called adiabatic shearing, keeping the tip sharp as it punches through. The fragments ignite on contact with air, turning the target's interior into an inferno. But that's not even the craziest thing that happens when the gun goes bang. When the pilot pulls the trigger, the gun pushes backward harder than a single engine pushes forward. Over 10,000 pounds of recoil against 9,000 pounds of thrust per engine. The aircraft literally decelerates while firing. So how do you aim something that's actively slowing you down? The engineers solved it by positioning the firing barrel, always the one at the 9 o'clock position, precisely on the aircraft center line. The gun itself is offset to the left, but recoil pushes straight back without yawing the nose off target. Pilots limit themselves to 2-second bursts. 2 seconds puts 130 rounds into a 40-foot circle from 4,000 feet of slant range. That's enough firepower to turn a city bus into scrap metal before you finish reading this sentence. And that precision exists for one reason: putting rounds on enemy armor without hurting friendly troops 100 meters away. Which is when the radio crackles with an update from the ground controller. The pilot keys the targeting pod and the battlefield appears on the display. The lightning pod beneath the fuselage combines infrared cameras that see heat signatures with daylight cameras that zoom from miles away, plus a laser designator for precision weapons. The A-10 carries no radar because it finds targets by looking at them, through the pod, through coordinates passed from ground controllers, through flying low enough to see what's actually happening below. The ground controller's voice comes through: coordinates, target description, location of friendly positions, enemy armor, 3 vehicles, grid reference follows. Friendlies are 200 meters south, cleared hot on arrival. 200 meters. That's 2 football fields between the target and the troops who called for help. The fire control computer is already calculating. Continuously computed impact point, CCIP, runs 60 times per second, accounting for altitude, dive angle, airspeed, wind, air density, and the ballistics of 30mm ammunition. A dot appears on the heads-up display showing exactly where rounds will land. That dot moves in real time as the aircraft maneuvers. Put the dot on target and the rounds go there. The system achieves 80% accuracy within a 40-foot circle from 4,000 feet of slant range in a 30-degree dive. That precision enables something bombs and rockets cannot do: danger close fire support. Danger close is the military term for situations where friendly troops sit so near hostile positions that the margin for error shrinks to yards. Mistakes take out your own people. Blast radii from 500-pound bombs extend outward in unpredictable patterns. Rockets carry the same problem. Only a weapon precise enough to land 130 rounds inside a 40-foot circle from nearly a mile away offers the surgical accuracy these situations demand. The target area appears on the horizon. The pilot calculates the geometry: dive angle for optimal accuracy, slant range for precision, burst duration for effect. Master arm on. Gun selected. The computed impact point appears on the display. Everything this aircraft was built for: the titanium bathtub, self-sealing fuel tanks, the redundant hydraulics, the engines that relight themselves. All of it comes down to the next 30 seconds. The pilot rolls the aircraft and pulls the nose toward the target. The dive begins at 8,000 feet, nose dropping 30 degrees below the horizon. Airspeed building through 300 knots. The computed impact point tracks across the heads-up display, a dot sliding over terrain towards the enemy vehicles while the pilot makes corrections measured in fractions of degrees. Slant range decreases through 6,000 feet. The strobes marking friendly positions glow on the targeting display south of the target cluster. 2 football fields between salvation and catastrophe. 5,000 feet. The dot settles onto the lead vehicle. 4,000 feet. Optimal range, the envelope where 80% of rounds hit that 40-foot circle. Trigger down. The hydraulic motors spin the 7 barrels up to speed in half a second. Then the gun fires. The vibration hits immediately. 10,000 pounds of recoil shuddering through the airframe 65 times per second, while the aircraft decelerates against both engines fighting the backward force. Rounds pour from the centerline barrel faster than perception can separate them. each one leaving at over 3,500 feet per second. 2 seconds, trigger release. 130 rounds have traveled downrange in less time than it takes to read this sentence. Gun gas washes back over the fuselage and the igniters cycle to keep the engines lit. The pilot pulls up, nose rising above the horizon, throttles forward to recover the speed lost to recoil. On the ground, the rounds arrive before the sound. 3,500 feet per second covers distance nearly 3 times faster than sound travels. The impacts happened in silence, then the noise reached the surface. The BRRRT, that sound exists because human hearing cannot separate 65 impacts per second into individual events. The brain blurs them into a continuous ripping roar that lasts exactly as long as the burst and then stops. It sounds less like a weapon than fabric tearing at impossible volume. Troops who hear it know one thing: they're not the target. If they were, they'd never hear it at all. Bye for now.